Remember? Yep. Okay. So last lecture we had stopped at this point. We were discussing the relationship between the sequence number in go back n and selective repeat versus the maximum window size a particular protocol can handle. And as we saw in the last lecture, with the same number of bits, go back n can handle a larger window size versus selective repeat. And again, just to repeat, if you have k bits for sequence number, then go back n can have n less than or equal to 2 raised to k minus 1 selective repeat and again, the reason you want to limit the window size is because you want the receiver to unambiguously interpret the data packets. You don't want to confuse between a retransmission and a fresh transmission. And because selective repeat handles more data packets at a time, it can process more data packets at a time, it expects more data packets at a time. Therefore, it's also likely to be more likely to be confused. So that's the reason why the maximum window size is smaller in selective repeat given the same size of sequence numbers. So why were we not happy with go back and why did we go to selective repeat? Performance. So how much better is the performance of selective repeat versus go back n? It's not an easy, it's not a simple question to answer. You can't just offhand say that it's 10 times better or 15 times better. So one of the things that we'll do today's lecture is I'll introduce you to simple performance analysis. When you're designing your own protocols, when you're designing your own systems, you'd like to understand how the system behaves, under different scenarios. So what we'll do today is we'll go through a simple exercise. We'll model the behavior of selective repeat and go back n, and under our model we'll perform an analysis of what the throughput is likely to be under the two protocols, and then we can do a comparison. So I mean, intuitively we know that the bandwidth requirements for selective repeat are going to be lower than go back n. So under what scenarios would selective repeat perform better than go back n? Suppose you have a perfect channel where nothing gets lost, nothing gets dropped. Is there going to be any difference between go back n and selective repeat? If nothing gets lost, yep, send this window of packets n and all of them reach the receiver. Is there going to be any difference between selective repeat and go back in? There won't be any difference, right? Because if there's nothing lost, nothing has to be retransmitted, the performance is essentially the same. You take a block of n packets, send it across, take the next block, send it across. So when does the performance start to diverge? When packets get lost. So an important factor that will differentiate the performance of the two is packet loss probability. So we know that packet loss will affect the performance. As packet loss goes up, the performance of selective repeat will be better compared to go back in. Why? Well, let's say you're working with go back in. You send this block of packets across and the third packet gets dropped. What is the behavior of go back in that scenario? Go back in will retransmit everything here. So at the sender end, sender would have to retransmit everything following the dropped packet in this block. Whereas if you were looking at selective repeat, if this packet gets dropped, the only overhead at the sender is to resend this particular packet. So you're saving on the overhead of these packets being dropped. And the average overhead would be you look at all the packets, look at the probability of each one in this window being dropped, compute the overhead, and look at the expected overhead. So clearly, as packet loss probability goes up, the performance of go back in is going to deteriorate. What other factor could affect the difference in performance of go back in and selective repeat? Yeah.
A lost acknowledgement.
Suppose the acknowledgements don't get lost, but that is sort of implicit in this packet loss. What other thing are we looking at when we're comparing the two? The window size. So the larger the window size, the more is the possibility of your wasted overhead. Suppose you're transmitting 1000 packets, your window size is 1000, and if the second packet gets lost, you have to retransmit 998 packets. But suppose your window size was only 4, then the worst case difference between selective repeat and go back in won't be a lot, right? There isn't much beyond the lost packet to retransmit. So the overhead of go back in increases as the window size is going to increase. Yeah.
It says a larger window. If there's no loss, can go back in perform better than?
No, if there's no loss, then both are the same.
But say there's, there is a large delay. It's not enough to time out, but they'll send more before waiting. I mean, if there's some sort of timeout,
Yeah.
it'll, its window will send more packets and selective repeats window.
If there is no loss, why would it send?
Well, if there's no loss,
Yeah.
if there is some sort of internet delay,
Yeah.
Selective repeats window is smaller, so it will only send a certain.
That's so cool. But selective repeats window is not smaller. You're talking about the relationship between the sequence number?
Oh, doesn't have.
No, we're assuming they can both have the same window size.
Okay.
And it's the same. So the overhead in selective repeat is adding more bits to the sequence number, right? And you can have the same window size. So there's a small overhead in the header. You're adding a few more bits. So instead of k bits, you need k plus 1 bits. So with one extra bit, you can handle the same window size. So that's not a critical performance issue. Okay, so intuitively we have argued that as packet loss goes up, the performance of go backend is going to become bad, and as the window size becomes larger, this n becomes larger, the performance is again going to become bad. So now let's try and develop a mathematical model for it and obtain quantitative answers which will support our intuition. So what's the model that we're looking at? So the model is very simple. Any packet which is transmitted on this unreliable channel gets lost with some probability p. We'll keep this loss probability p a constant. We assume that acknowledgements never get lost. For selective repeat, our model is that the sender will know exactly what the receiver needs. So it will retransmit only packets which got lost. It will assume that the out of order packets are buffered by the receiver. That's the model for selective repeat. Go back and we model it this way. In each round, the sender will transmit n packets, which is our window size. Receiver will inform the sender of the first lost packet in that block. Then the receiver informs the sender of this first lost packet. After that, the sender will send n packets starting from this first point of loss. So what that means here is, suppose this third packet got lost and we are working with go back n. So now when the sender comes to know that this packet got lost, it's going to transmit n packets starting from this one. So it will know that these first two packets have already been delivered. So it moves its send base forward and it will add two new packets and send them across. So in each round is going to send across n packets. And the starting point of each round is decided by the knowledge of the first loss. So that's our simplified model for the two protocols. Now in selective repeat, because each packet has the same probability of loss p, and because the receiver can inform the sender exactly which packet got lost, we can examine each packet in isolation. So what do I mean by examine each packet in isolation? We look at this quantity called TSR. TSR is the number of times a packet has to be transmitted in selective repeat. Okay. So the first equation here says probability of TSR being greater than I is p raised to I. Why is that? Well, you send one packet across. We say the channel loss probability is p. So with probability p, it's going to get dropped, and with probability 1 minus p, it's going to get delivered. Okay. Now for the number of transmissions to be greater than some I, it has to be dropped at least I times. Right? For the number of transmissions to be greater than 1, the first transmission has to be dropped, otherwise it's successfully delivered. For the number of transmissions to be greater than 2, the first 2 transmissions have to be dropped. And what is the probability of that event? Probability of the first transmission getting dropped is P. Now since the next packet that is sent is like an independent packet, an independent experiment, that probability becomes 2 if the number of transmissions has to be greater than 2, and so on and so forth. So each time the packet gets dropped, it has to be retransmitted, and the probability of more than I transmissions is Pi, P raised to I. Okay, we're clear so far? Now what we're going to do is, we're going to compute the expected value of this number of transmissions. Expected value or the average value. So what is that average value? That's probability number of transmissions is 1, weighed by 1. Probability number of transmissions is 2, weighed by 2. Probability number of transmission is 3, weighed by 3, and so on. This can be transformed into this equation. Is this step clear? Why that happens? The probability that you're looking at here in this expected value is the probability of the transmissions being exactly 1, exactly 2, exactly 3, and so forth. Whereas the probability here is greater than 0, greater than 1. So what is the probability of the transmission being exactly or greater than 0? The probability of transmissions being greater than 0 is the probability of transmission being 1, being 2, 3, so forth. So you take one term from each of these terms. And you can simplify this first line into this line. This is a simple geometric series given that probability TSR greater than I is Pi, and you obtain this formula. So the expected number of transmissions for a packet in selective repeat is 1 over 1 minus P. So if P is 0.8, the number of transmissions is 5. So this formula also makes intuitive sense. If the loss probability is 0, your number of transmissions is going to be 1. Nothing gets lost. If the loss probability approaches 1, then the number of transmissions approaches infinity. Because every time you send something, it gets lost. So this is the number of transmissions in our model of selective repeat. So each packet has to be transmitted on an average 1 over 1 minus P times. That is the overhead. Okay? Now let's look at an analysis of go back N. So in go back N, we define this quantity Sn, which is the number of packets which arrive prior to a loss in a window of N. So in this scenario, if the third packet or the first packet which got lost, then in the first round Sn is going to be 2. If the fifth packet was the first packet which got lost, Sn is going to be 4. So Sn Sn is keeping a count of the number of packets that were successfully transmitted across and delivered by go back N to the upper layer. Because these packets might have been transmitted, but go back N is going to drop them. Okay? So Sn is keeping a track of the number of packets which are successfully delivered to the receiver in go back N. Now what is the probability Sn is greater than I? So again, it's similar to the analysis we did with selective repeat. We treat each packet in isolation, but now these are separate packets in the window. So for Sn to be greater than I, it means greater than I packets in sequence have been delivered. What is the probability of one packet being delivered? 1 minus p. So the probability of greater than I being delivered is 1 minus p raised to I plus 1. Is this factor clear why we have this? Sn counts the number of successful deliveries in your window size of n. So for Sn to be greater than some I, it's the probability of successful delivery of an individual packet raised to I plus 1. The other thing here is that this I is bounded by n, because your Sn can never be greater than n. You're sending n packets in a window. So again we do the same analysis. We want to compute the expected or the average value of Sn. And the analysis that you saw in the previous slide, you do the same thing. Expected value of Sn is 1 times probability Sn equals 0 plus 2 times probability Sn equals 1, and so on and so forth, which is simplified to this equation. Now this again is a geometric series, but it's a finite geometric series, sum of a finite geometric series, because there are finite number of terms. N is finite, and the sum of this finite geometric series is given by this quantity. So that gives you the number of packets arriving prior to a loss. But we are not done yet. Now if you go back and see our model of go back n, in each round the sender is going to transmit block of n packets. When the receiver is informs the sender of the first lost packet, the sender will send n packets again. So in every round the sender keeps sending n packets. Some of them are fresh packets, some of them are retransmissions. So let J denote the round of transmission of these n packets, then Snj is the number of packets which are accepted in the jth transmission. Okay. Now again this Snj will consist of some fresh packets and some packets which were retransmitted but were not accepted in the previous transmission. Now we are going to compute the same quantity, which is the average number of transmissions of a packet. So first let's look at this term here. If you have m transmissions, So you're sending m blocks of n packets. So if you have m rounds in which every round you're sending n packets, what is the total number of packets that you have sent out? M times n, right? You have m rounds. In each round you're sending out n packets. You have one round, you send out n packets, another round you send n packets. So the number of total packets, if you have gone through m rounds, is m times n. The quantity in the denominator is the number of packets which are accepted by the receiver in the jth transmission. Okay, that's what we said SNJ is. In every round, if you send m packets, if you send n packets, Sn is the number of packets which are delivered successfully. After the Sn, after Sn, everything is dropped by the receiver. So in every round, Sn, comma j are the number of packets that are delivered successfully. So if you look at this ratio, this gives you an idea of the number of retransmissions. Right? You have transmitted m times n packets, but the number of packets which have been delivered successfully is this quantity. If these two quantities were exactly equal, that means there has been no retransmission. Everything you transmitted got delivered successfully. But in practice, the numerator is going to be higher than the denominator. And this ratio gives you an indication of the number of retransmissions. So what you do is you multiply and divide both numerator and denominator by m. The numerator becomes exactly n. What is the denominator now? The denominator is the average value of Sn over m rounds. Right? The average number of successful deliveries in m rounds. If you let this m go to infinity, then this quantity becomes the expected value of Sn. This is the result of an experiment, and this is the expected value of that experiment. I'm assuming you're familiar with the notion of an expected quantity, right? It's a mathematical average, whereas this is what you get in an experiment. So when you do that, when you let m tend to infinity, you get n over expected value of Sn, and that is the expected number of transmissions in go back n. And you get this formula. Now we can compare the performance of go back n and selective repeat, and we can vary these two parameters, the loss probability and the window size. So what I'm plotting here is the expected number of transmissions for go back n divided by the expected number of transmissions for selective repeat. On the x-axis, we are varying the loss probability, and the y-axis is that ratio, expected number of transmissions of go back n over selective repeat. And as you can see, as you increase the loss probability, the expected number of transmissions is going to go up, which is what our intuition was. If the channel is more lossy, then the performance of selective repeat is going to be much better. The other thing is, as your window size grows, the performance of selective repeat becomes much better. So if your window size n was 1, then selective repeat and go back n are no different, right? If your window size is 1, then it doesn't matter whether you're implementing go back n or selective repeat, the performance would be the same, and that is shown by this red curve. The ratio is always going to be 1. When you start increasing the window size, if you go to 1000, then at loss probability of 0.5, the performance of selective repeat is almost 500 times better than go back n. So both of our intuitions, just by looking at the protocol, that selective repeat becomes better as loss probability rises, and selective repeat becomes better as the window size increases. Both of them are confirmed by this simple analysis. So any questions here? So again, I mean, the book is very good in explaining a lot of concepts, but the book doesn't do a lot of analysis, and often it helps to analyze what's going on, to build mathematical models, to understand the physics of the system. So this is a simple example that we went through of protocols that we looked at, and how can you model the protocols mathematically, how do you vary parameters and understand the behavior of the protocols. We'll probably go through a similar exercise to understand the performance of TCP. Now these are abstract protocols, TCP is a real protocol, and we'll see if we can model the behavior of TCP and understand its performance. How do things like round trip time or loss affect the performance of TCP? Okay. So far in this chapter, what have we done? What have we learned so far? We've learned 3 things: that the transport layer, we've learned what kinds of services the transport layer can provide, and within that we have looked at the concept or the notion of multiplexing and demultiplexing. The other thing that we have looked at, which is not specific to transport layers, but on the internet it's provided by the transport layer, is this concept of reliable data transfer. We looked at reliable data transfer protocols, assuming an unreliable communication channel. We looked at ways to implement reliable data transfer and ways to improve the performance by using windowed protocols. So those were abstract concepts. Now we go and look at TCP and see how those concepts have been implemented in TCP. 2 things that we spoke about earlier, which we haven't discussed so far, flow control and congestion control. So both flow control and congestion control, we'll look at how it's implemented in TCP to get a better sense of the concepts that are relevant there. Okay, so let's start with TCP. These are the various RFCs which define TCP and the variations and improvements that have happened to TCP over the years. TCP, originally in the Internet Designer, if you have heard of ARPANET, TCP and IP were part of the same protocol. And I think in the late 70s or early 80s, TCP and IP broke off. The responsibilities were separated between IP and TCP. But because of that, the name sort of has carried over, and we still talk of TCP as TCP/IP. The two are sort of intimately tied together. They used to be one protocol, then they broke off. So we'll look at what IP does when we get to the network layer. TCP operates in the transport layer. So TCP, first of all, is a point-to-point protocol. It has exactly one sender and one receiver. So things like multicast cannot be implemented using TCP. TCP provides reliable in-order byte stream. There are no message boundaries in TCP. It just provides a stream of data. TCP uses a pipelined protocol to transmit data. Pipeline protocols are the go back N and selective repeat kinds of protocol that we saw. And the way congestion and flow control is implemented in TCP is by adaptively changing this window size. The window size that we dealt with earlier and which we analyzed, that we assumed the window size to be some fixed N. The way TCP implements congestion and flow control is by adaptively changing this N. The higher your N, the faster you can transmit data. But if there's congestion, you have to reduce your N. So both flow and congestion control are implemented by adaptively changing this N. In TCP, both at the sender side and the receiver side, there is a buffer. So the buffer buffer exists in the transport layer. Application writes data to the transport layer. In the transport layer, there is a buffer of some finite size. And before TCP can send out that data onto the channel, that data is stored in this send buffer. And similarly, there is a receive buffer. Before the application can be delivered the data, TCP stores whatever it has received in this receive buffer. And these buffers are very important for the performance of TCP. TCP is a full duplex connection. So once you establish a TCP connection, there is bidirectional data flow on the same connection. So in the examples that we were looking at, we always had a well-defined sender and a well-defined receiver. In a TCP connection, once your connection is established, data flows bidirectionally. There is no notion of a sender and a receiver. We'll get to the connection oriented bit later. There is a maximum segment size associated with TCP, which is the maximum size of the packet. Okay, so we say that TCP uses pipelined. TCP is pipelined, so it uses these sliding window protocols. what are the essential features of a sliding window protocol? What do you need to implement if you want to implement a sliding window protocol? What are the features that you need to implement at the sender, receiver, or in the headers? I'm sorry? So you need the window and you need the acknowledgement. Sequence number. Yeah, that's what I was looking for. You need sequence numbers and you need a way to implement acknowledgements. Okay, so those are two essential characteristics of a pipeline protocol. So we now do you foresee any problem of implementing those sequence numbers and acknowledgements the way we have studied so far with TCP? There is a slight complication, which is because in TCP there is bidirectional data flow. Right? Data can flow in both directions, so you need to have sequence numbers in the forward direction and in the reverse direction, and also acknowledgements in the forward and reverse direction. So the way it's implemented is, first we look at the segment structure, and then we'll see how this acknowledgement and sequence numbering works. The TCP segment structure looks like this. The width of this segment is 32 bits. You have 16 bits assigned for the source port and the destination port number. That's necessary for multiplexing and demultiplexing. Then you have 32 bits assigned for the sequence number. Remember, you have a sliding window protocol, so you do need sequence numbers, and the number of bits that are assigned are 32 bits. There is an acknowledgement number field, again 32 bits. There is a field called receive window. Receive window indicates the number of bytes a receiver is willing to accept. So the receive window also gives an indication of how large the buffer is at the receiver end. If you're, let's say, operating a PDA, your buffer size is very small, and that has implemented TCP, then the receive window field for that PDA is going to be very small. Whereas if you have a desktop or workstation, the receive window can be large because you can absorb data faster. So flow control is implemented through receive window. We'll look at the details later. This is a field header length, 4 bits, I think. I'm not sure. You can look up those details in the textbook. There's one field that is not used, and there are other bits which identify what kind of packet it is. There is a field for checksum, the same as UDP. TCP can have a variable number of options. So these are all 32-bit wide options, and the number of options is defined by this header length field. So you can have number of different options which sort of enable some modifications of TCP. The sender and receiver can communicate, and the behavior of TCP can be changed a little bit depending on these options. So This options field is variable length. You can have a number of these 4-byte length options in a packet. After the options follow the application data. So this is the TCP segment structure. These bits indicate what kind of a packet it is. For connection establishment and connection tearing down, you need a special kind of packet, and that's identified by those bits. So when you get to the connection establishment, we'll look at what those signify. Now this slide explains how the sequence numbering and acknowledgements work in TCP. So this is where some of the complication comes in. Since TCP, the data transfer is bidirectional. In TCP, often the acknowledgements and data packets get piggybacked on each other. So the data packet itself carries the acknowledgement. So what's happening here? Well, first, the sequence number in a TCP segment is the number of the first byte in the segment's data. So your packet will contain a number of bytes which you are trying to deliver. The sequence number is going to be the first byte stream number of the first byte in that packet. The acknowledgement is the sequence number of the next byte which is expected from the other side. And the way ACKs are implemented in go backend, TCP implements cumulative ACKs. So any acknowledgement acknowledges everything that has come so far. Now let's see how this works in practice. What's being shown here is a remote login session which is using TCP to transmit data back and forth between the remote machine and the machine where you have logged in from. So suppose you have a desktop in your dorm room and you have logged into the CS Unix account. So how does that process work? You have maybe a telnet window open, you have SSH onto the server, and when you type something on your desktop, that character has to be transmitted across the network to the server, to the Unix server. So when you type C on the desktop, the byte representing C has to be transmitted across to the server. So the C has a sequence number 42. Let's say it was the 42nd byte that you sent across from your workstation to the server. So the sequence number, which is the first byte here, is going to be 42. ACK represents the next byte that you are expecting from the other side. So that's the ACK field, and the data is going to be the character C. This host will then receive this C and it echoes back C. So the character C appears on the terminal and it's echoed back by the server. So server is now going to send back this data packet C. You typed on your keyboard that C character went across to the server. The server interpreted C and it sends back to your terminal. Right? When you are doing this remote login session, when you type any keystroke, it is not instantly echoed because it has to be correctly interpreted by the server, and depending upon what key, what program you're running, the server has to take the right action. So the first transfer was the transfer of your hitting the keystroke and that information going across. Then the server receives this C and it's simply echoing back. So on your screen you'll see a C. So now look at what that packet looks like. The sequence number is now 79 because 79 was the ACK field of the previous packet. This is now this user or this host A is expecting a packet with sequence number 79. So that's what's sent across, and ACK is the sequence number of the next data segment that it's expecting, which now becomes 43. Yeah.
We were going to talk about the development kit.
Yeah.
So in this case, we are assuming the buffer is equal to one character.
It's at least one character.
So it can now, in a period of time, if it doesn't fill out the buffer before it sends it.
No, sorry.
Because if you have to send the buffer, it's why you send across the channel.
So you're talking of the send buffer or the receive buffer?
On the send side.
So send side, you're assuming that the channel is free. Why would you wait on the send side if the channel is not free, or if there is some error or retransmission needed?
So you need to have the buffer.
Yeah, for now ignore the buffer. Ignore the buffer. So what happens is one byte is sent across with sequence number 42. It's received here. Since sequence number 42 is received, this next packet will carry an ACK number 43. It's expecting byte 43 in the next time A sends something to B. And this process then carries on. The host will acknowledge this receipt of this echoed C with the sequence number 43 and ACK 80. Now in this packet there is no data. It's simply acknowledging what was sent here. So you're seeing different kinds of packets here. You have two data packets which both carry sequence numbers and acknowledgement numbers. Then you have a pure acknowledgement packet. It doesn't have any data. It's simply acknowledging the last packet which was received. So if you have data to send, then you piggyback acknowledgement with the data packet. If not, then you have to send an ACK back in any case. And because it's bidirectional, each packet contains both the sequence number and the ACK number. In our earlier examples, the forward packets carried the sequence numbers and the acknowledgements in the backward directions carried the ACK numbers. Here, because data transfer is happening in both directions, in TCP every packet will have a sequence number and an ACK number. Now another thing that we needed to implement these sliding window or pipeline protocol was we had to implement the functionality of timeouts. Right, if something got lost and something had to be retransmitted at the sender's end, you needed to implement timeout mechanism. To implement timeout mechanism, you need to set the timeout value. So how do you set the timeout value for TCP? Well, in our discussion earlier, a couple of lectures ago, we agreed that it has to be longer than the round trip time. Round trip time itself will vary or fluctuate. If we keep the timeout value too short, it'll cause premature timeouts and it'll cause unnecessary retransmissions. Even though packets are reaching, because our timer value is too short, things would time out and there'll be unnecessary retransmissions. If it's too long, then our reaction to a segment loss is going to be very slow, and that will also affect performance. So we'll see what the choice was for TCP. In setting this timeout value. So first, to set this timeout value, it has to be related to the round trip time. And how do you get an estimate of the round trip time? Well, you measure the time between sending a segment and receiving the acknowledgement. So you can timestamp when you send out a packet, and when you receive the acknowledgement for that packet, that gives you an estimate of the round trip time. So in this example, the round trip time is going to be this time. When you sent out the sequence number 42 and until you got the acknowledgement for that sequence number 42. So this is going to be the round trip time. You can measure the round trip time at the end host by simply keeping track of when you send the packet, when you got the acknowledgement back. This sample round trip time is going to vary. So you want the estimated round trip time to be smoother. So you're going to average several of these measurements. If you have a long enough connection, you're going to send several packets across. You're going to get several acknowledgements back. You'll have several samples. And you average out these samples to get a better estimate. The formula that is used to get the estimate of the round time is, you have the old estimate of the round trip time, you multiply that by 1 minus alpha, and you add to that alpha times your new sample. So every time you get a new measurement, you get a new ACK back, you're going to get a new estimate of the round trip time. So you're going to get a new sample. And you update your estimate by this formula. This is a well-known averaging technique called exponential weighted moving average. And what it does is that the influence of past samples decreases exponentially fast. So this technique forgets history. It keeps sort of a moving average and it starts forgetting history very fast, exponentially fast. And it depends on what the value of alpha is. Typical value of alpha is 0.125. So here is an example. The blue points here are the sample round trip time values. So every time you sent a packet and got the ACK back, you got a sample. The sample round trip time varies a lot, from slightly below 200 milliseconds to above 300 milliseconds, because an individual packet might face queuing delay, it might get dropped in the link layer, get retransmitted, several things can happen. So the sample round trip time is going to fluctuate a lot, and the purple curve is the estimated round trip time computed using the exponential weighted moving average. So that's going to be smooth. It's a smooth average tracking the variations. Do you have a question? Is this clear? Or is it? Yeah.
Just thinking about other things. Just thinking about how people modify this to keep a history, so maybe we could get it from maybe the application because you want a more stable graph on this. Like if you get a ping, it changes the graph pretty drastically.
Well, we can change how fast this graph changes by changing the alpha. If suppose you kept alpha as 1, What would that imply? That would imply that your estimated RTT is simply the sample RTT. So it will track it really fast. If alpha is 0, then it will just ignore the samples. So the higher the alpha, the faster it tracks. And the smaller the alpha, the smoother is the average. So this gives how to compute estimated RTT. But we are not done yet. We want to set the timeout value, which is related to this estimated RTT. And how is it related? It's estimated RTT plus safety margin. So first you estimate how much the sample RTT deviates from the estimated RTT. And that deviation again you obtain as a moving average. You have another parameter beta. You have an estimate of the deviation, and to that you add a new sample of the deviation. So you get a new sample of the round trip time. You already know what the estimated round trip time is. You look at how much the sample varied. That gives you a new sample of the deviation, absolute value. And then you smooth out that deviation. So now you have a smoothed out round trip time and a smoothed out deviation. And the timeout interval is that estimated RTT plus 4 times the smoothed out deviation. That's what TCP typically implements. So the deviation measures how much it's fluctuating, how much those blue points are fluctuating from the purple curves. The higher the fluctuation, the higher is going to be the deviation. So the more you need the safety margin to be. The smaller the fluctuation, the smaller the safety margin needed is. Why don't we keep the timeout value to be some fixed number? Yeah.
Flow control. It'll adjust how much it's sending to
Not really. It's the picture times might change depending on the conditions. Round trip times
Change depending on the network conditions and depending on where you're connecting. Right? The round trip time, the connection between here and my desktop in my office is going to be microseconds. But a connection between here and CNN.com in Atlanta is going to be tens of milliseconds. So the round trip time that is appropriate for this local connection is not appropriate for other connections. That's why on a per connection basis, you measure things, you estimate them, and it also factors in the local network conditions. So these fluctuations reflect what's happening in the network locally during the time of that connection. That's why you measure things on a per connection basis and keep these values. Somebody had a question here? Or? Yeah.
Initially, what would we use to set up the estimated RTP?
Okay, good question. So,
What is the first value here? So the first value that is used is depending upon the implementation of TCP. They start with the first timeout value, I think, is 500 milliseconds, default value or something like that. But as soon as you start getting samples, you forget history. So it gets averaged out. So there is a default value that you start with, but very quickly the connection forgets that default value and adapts to the right value. Now, as we have said earlier, TCP implements reliable data transfer. TCP creates this reliable data transfer on top of IP's unreliable service. We have already seen that all the things that are needed to implement reliable data transfer are in place with the TCP segment structure. We saw that it does pipelining, we saw that it does sequence numbering and acknowledgement numbering, we saw that it implements timeout. So TCP has pipeline segments, cumulative acts. We saw how the timeout values computed. To get an idea of what the TCP's reliable data transfer mechanism looks like, we'll get into the details of that, but initially we consider a very simplified TCP sender. So we're going to ignore the flow control and congestion control aspects of TCP. Assume that TCP is working with fixed window size. So what are the events that can happen at the sender? Well, again, three events which we saw in the reliable data transport protocol. You can either receive data from a higher layer. In the case of TCP, it's data from the application layer. You can have a timeout, or you can receive an acknowledgement from the network. Those are the only three events that can happen. So if you receive data from the application layer, you're going to create a segment with the right sequence number. We already saw what the sequence number looks like. It's the first data byte in the segment. If a timer is not already running, you're going to start a timer. So TCP implements only one timer. So you can think of the timer as the timer running for the oldest unacknowledged segment. So if a segment is out for which you have already started the timer, then you don't need to restart the timer. So in selective repeat, we needed timers for every packet, which could be an implementation headache. TCP, you need only one timer. The expiration interval of this timer is the timeout interval, which we saw how TCP computes. When the timer does expire, this event happens, then you're going to retransmit the segment that caused that timeout, and then you restart timer. When you receive the acknowledgement at the sender, if the acknowledgement acknowledges previously unacked segments, then you update what is known to be acked, so you can move your send base across, you can send out fresh packets, so the sender knows what the receiver has received, and you start a timer if there are outstanding segments. So what does this mean? This last part, remember TCP has only one timer, and that timer is for the oldest unacked segment. Once that unacked segment is acked in this step, then you restart the timer if there's something outstanding. Yeah.
Have maximum number of retransmissions per packet. And you're sending it, you get timeout.
Yeah.
Then you send it again, you get timeout.
So are you saying does TCP keep on trying, or is there a finite retry limit? It's implementation dependent. I don't think any RFC specifies that you have to retry 7 times or 50 times. TCP will just simply keep on retrying.
The other side just went down.
Yeah, so then there has to be a higher level timeout, some other layer. The application at some point gives up. And it'll tell TCP, okay, don't try it. So this is the pseudocode of the behavior of the TCP sender. Again, the three events: data received from application, timeout, and acknowledgement received. And the pseudocode explains what are the steps that are taken, each of the three events. The retransmission scenarios are shown in this slide. So in one scenario, the acknowledgement gets lost and the packet has to be retransmitted even though it was delivered. In the other scenario, the acknowledgements simply get delayed. Your timeout value was here, but the acknowledgements arrive later. So again, packets have to be retransmitted even though they were successfully delivered. Now, okay, in this scenario, suppose your timeout interval was somewhere here. Your timeout interval was here. This ACK got lost. Would TCP retransmit this segment? No. Why not? Cumulative ACK. Because the second ACK went through. Losing this ACK wouldn't harm you. This ACK says that, okay, I've received everything until byte number 119. I'm expecting byte 120. This ACK was simply saying I've received everything until byte number 99. Once this ACK arrives, the sender knows that the receiver has received everything up to byte 119. So TCP is somewhat robust to the loss of acknowledgement segments. Now these are pure ACKs. These are not piggyback ACKs. Yeah, this is explaining that scenario. We'll carry on in the next lecture and start with flow control and congestion control.